Hello everyone, welcome back to this week's algebraic graph theory seminar. This week we have Qianqian. She's going to talk about the sesqui-regular graphs with fixed smallest eigenvalue.
So it's okay for me to start now, right? Can you hear me well?
Yes.
Okay. I'm from Shanghai University. Now I'm a lecturer here. Today I'm going to talk about sesqui-regular graphs. This work is done about 2 years ago, but we have never given a talk before. And the paper is still under review. So this is somehow quite new result. My talk will consist of 3 parts. In the first part, I will give the definitions and the motivation. In the second part, I will give the proof. And in this part, I mainly introduce the tool we use because it's not so many people are using Hoffman graphs as a tool to study graphs with fixed smallest eigenvalue. So I will spend quite a lot of time on the second part. In the third part, I will show the new finding and propose few questions. Now I start the first part. Before going to introduce strongly regular graphs, I will give few notations I will use in the talk. In this talk, all of the graphs are finite, undirected, and simple. And give such a graph G, we denote by Vg its vertex set and Eg its edge set. And we use Aj to denote the adjacency matrix. And the smallest eigenvalue of this graph means the smallest eigenvalue of its adjacency matrix. And we use lambda minimum J to denote this smallest eigenvalue. And also, if H is an induced subgraph of J, I will write it like H is somehow subset of J. Otherwise, I will use the H is not a subset of J if H is not an induced subgraph of J. And finally, I will just notice that a graph J is K-regular if our vertex of J has valency K, although the last one is very trivial for us. Now I start to remind the strongly regular graphs. Strongly regular graph is a very common notion in our area. A graph G is strongly regular with parameters V, K, A, C. It means that this graph has V vertices. It is K-regular. Every pair of adjacent vertices has exactly A common neighbors. And every pair of distinct non-adjacent vertices has exactly C common neighbors. Here I gave a picture with 5 vertices, and every vertex has valency 2. And if we find a pair of adjacent vertices, they have no common neighbor. And if we find if we find 2 non-adjacent vertices, then they have exactly 1 common neighbor. So the graph in this page is a strongly regular graph with parameters 5, 2, 0, and 1. And for strongly regular graphs with fixed smallest eigenvalue, we have such results. We knew that for strongly regular graphs, either it's a convergence graph or its smallest eigenvalue is an integer. So we assume that lambda is an integer. If J is a connected strongly regular graph with parameters V, K, A, and C, and its smallest eigenvalue is minus lambda, then we knew that J is either a completely multipartite graph, or the parameter C is bounded by lambda. Also, there is another result says that J is a completely multipartite graph, a Steiner graph, a line square graph, or J is in a finite set. If you are interested in the details of the proofs, you can read the paper by Neumaier. He gives the proofs, especially in the result 2. For the case where J is in a finite set, she gave a bound on the numbers of J. So, if you are really interested in how he showed these results, you can read his papers. And in the paper, the graphs must be strongly regular. He used a lot of properties strongly regular graphs have. So from the definition of strongly regular graphs, we knew that it has very strong conditions. So we are thinking whether we can weaken the conditions of strongly regular graph and study some graphs new. So this is the first graph come to our mind. A graph G is co-edge regular with parameter VKC. It says that this graph has V vertices. It is K regular, and every pair of distinct non-adjacent vertices has exactly C common neighbors. From the definitions, we can say that the co-edge regular graph is a larger class of graphs than strongly regular. It does not force the adjacent vertices has fixed common neighbors. Here, I also gave a picture and show an example of co-edge regular graphs. For these graphs, we can see that there are 4 vertices on the left, and there are another 4 in the right. And for the vertices in the left and right, they are pairwisely adjacent. And the left is 2 edges, and the right is also 2 edges. And we can check whether this graph is co-edge regular or not. First, it has 8 vertices, and every vertex has valency 5. It has 1 neighbor at the same side as another 4 neighbors in the other side. And for any 2 non-adjacent vertices, it has exactly 4 common neighbors. So after checking the conditions, we see that the picture here, it shows a co-edge regular graph. I also want to say that this co-edge regular graph is not strongly regular. If we look at the 2 adjacent vertices on the same side, for example, the left side, it has 4 common neighbors. But if we look at the 2 adjacent vertices in different sides, it has only 1 common neighbor. So it's co-edge regular, but it's not strongly regular. So for the co-edge regular graph with fixed smallest eigenvalue, here is a result. Give a real number lambda. We can find a constant relative to lambda. Let's say C1 lambda. It says that if J is a connected co-edge regular graph with parameter VKC, and its smallest eigenvalue is at least minus lambda, then either V minus K minus 1 is bounded by lambda, or C is bounded by a function of lambda. This is a result by Qianqian and Professor Jack Koolen, and this is the application of their studying on the order of regular graphs with fixed the largest eigenvalue. In this paper, they also use the tool in this talk. So if you are a little if you are a little curious about how they show the results, you can also read this paper. In this talk, we studied a more generalized, more larger class of graphs, because in the definition of co-regular graphs, the condition 3 says that every pair of distinct non-adjacent vertices has common neighbors. It says that a co-regular graph must have diameter at most 2. So we want to study a more wider class of graphs. So we generalize the condition 3 and have new graphs. This is the sesqui-regular graph. It's also the graphs mentioned in the title of the talk. A graph G is sesqui-regular with parameters V, K, C. If this graph has V vertices, it's K-regular, and every pair of vertices of distance 2 has exactly C common neighbors. We say that the condition 3 is a weaker version of the condition 3 for co-regular graphs. Here, I also gave a picture which shows a sesqui-regular graphs. Here we can see that this graph has also 8 vertices, and every vertex has valences 3. And if we check it carefully, we can see that every pair of vertices of distance 2 has exactly 2 common neighbors. Also, we can find that this graph has diameter 3, then it's not quite regular. So there are many graphs which are sesqui-regular but not quite regular. For sesqui-regular graph with a fixed smallest eigenvalue, we have 2 results. The first result is very similar with the result for co-regular graphs. It says that to give a real number lambda, we can find a constant C2 lambda such that if G is a connected sesqui-regular graph with this parameter and the smallest eigenvalue is at least minus lambda, then either V minus K minus 1 is bounded by lambda or C is bounded by a function of lambda. It's very similar with the result for co-regular graphs. So you can imagine that you can prove it by the same method as for co-regular graphs, and the guess is correct. That's why I mentioned this paper when I introduced co-regular graphs, because we can really use the same method to obtain the same result for sesqui-regular graphs. This is not the result I wanted to show in this talk. So somehow this result is better to be in the talk related to the paper by Qianqian and Professor Koolen. The result I want to show in this talk is another one. This is the second result in this paper. It says that if the valency of the sesqui-regular graph is very large, for example, it's at least somehow we can find a constant kappa y lambda such that the valency of this sesqui-regular graph is not less than kappa y lambda. Then we can give a more precise upper bound on the valency C. This is our result. So in this result, we really need the condition that the valency is very, very large. And compared with the previous result, in the previous result, we just say that C is bounded by a function of lambda. Then in the second result, we say that if the valency is very, very large, then we can give a more precise upper bound on the parameter C. So actually, result one can be easily obtained from the result two. You can, if you are interested, you can try it. You can try to do it. This is the second result in this paper, and this is also the result I want to show how to prove in this talk. Now I'm going to introduce the method we use to prove this result. Before going to do it, let's start with two interesting graphs. There is a very something like fundamental result. It says that give an integer lambda. If G is a graph with smallest eigenvalue not less than minus lambda, then G cannot contain a graph with smallest less than minus lambda as an induced subgraph. This is somehow like an interlacing result, and it's we usually use in algebraic graph theory. So here it says that if the graph has the smallest eigenvalue at least minus lambda, then it does not contain graphs with smallest eigenvalue less than minus lambda as an induced subgraph. So I want to show two important graphs with the smallest eigenvalue as small as possible. The first one is the claw graph. The claw graph Q1T, I mean a vertex adjacent to 2T, pairwisely non-adjacent vertices. For example, here I give a claw graph K13. When you maybe we can do it by ourselves to show that the smallest eigenvalue of K1T is minus square T. And if T goes to infinite, this graph has the smallest eigenvalue goes to minus infinite. This is the first graph with the smallest eigenvalue can be as small as possible if T is large enough. And the second graph is not common. This graph first occurs in Hoffman's paper in 1973. This graph denoted by tilde K2M. It means it's a graph with 2m plus 1 vertices. And the 2m plus 1 vertices consists of a clique K2M and another vertex, which is adjacent to exactly m vertices of this clique. This is a graph K2M tilde. Here I also showed the picture the K6 tilde. K6 tilde is a clique with 6 vertices and one more vertex adjacent to half vertices of this clique. Here, adjacent to 3 vertices. This is K6 tilde. If you want, you can also show that the smallest eigenvalue of this graph also goes to minus infinite if m is sufficiently large. So we can imagine that. Sorry. Sorry, I made a small mistake. So let's give a graph G with smallest eigenvalue at least minus lambda. From the previous page, we knew that the smallest eigenvalue of KYT can be very small. So we can find a T lambda such that the claw graph Q1T is not an induced subgraph of G if T is very large. If KYT is not an induced subgraph of G, this means that if the valency of this graph G is very large, then we give a vertex of G, let's say X. Its neighbor, it has many neighbors. And in these neighbors, it does not contain a clique, but it does not contain an independent set of sets T. Then it must then use the Ramsey theory. We knew that in the neighbor of X, it must contain a very large clique. This is the Ramsey theory tells us. So the claw graph is not an induced subgraph of G. Implies that we can always find a very large clique in this graph if the valency of this graph is very large. Then if we have many large cliques, what can we do? This is how we use the second graph. When the tilde graph K2M tilde is not an induced subgraph of G, then we can have an equivalence relation on the large cliques of G. This is how we give the equivalence class on the large cliques. We use the Cn denote the size of maximum cliques of G of order at least n. Here we need n is at least n+1 square. When the tilde graph K2M tilde is not an induced subgraph of G, then we can have an equivalence relation on the set of maximum cliques Cn. Here is how we give the relation. We say that the two cliques have a relation if every vertex in C1 has at most n-1 known neighbors in C2. Here I just gave the relation for the two cliques for I just gave the condition for these two graphs has a relation, and it's not hard to show that this is an equivalence relation. With this equivalence relation, we can go one more step. We knew that for the cliques in a same equivalence class, it's very dense because it has only few known neighbors in another big clique. So we can do more steps to define this dense graph. Give a clique C in this set, let's say Cn, then we can define a dense graph. We call the crazy clicks. The crazy clicks is the subgraph. Is the subgraphs induced on the vertices which has at most n-1 node neighbors in C. If it also can be checked that this definition does not related to the it's well defined. It's not dependent on the choice of the choice of C. It means that you can find another click in the same equivalence class of C, and the crazy click, the definition of or the crazy click is same. We will not have different crazy clicks. The crazy click is somehow the most, let's say it's a main notion in this talk. We want to say that this crazy click it means that for two vertices in a same crazy click, they must have many common neighbors. Because for two vertices in the same crazy click, they both adjacent to many vertices in a large click. This is what I wanted to say. And use crazy click, we can have we can go to the associated Hoffman graph. This is also showing the outline. Because I want to emphasize that we have the equivalence class, we have the crazy clicks. The first condition is the K2M tilde is not an induced subgraph of J, and the N is at least M plus Y square. This is the precondition. Without these two, we cannot have equivalence class. We have no crazy clicks. So I emphasize the conditions here again, and assume that C1, C2, and CT we assume that under this equivalence relation, we have T different equivalence classes, and then we can add T different, not different T special vertices. Let's say F1, F2, F2, Ft to G, such that these T special vertices are pairwisely not adjacent, and for the vertex Fi is adjacent to all of the vertices in crazy clicks QCI. So here I want to say that these T vertices are special. This is different from the original vertices. After doing this, we obtain the associated Hoffman graph. A Hoffman graph, let's say a Hoffman graph is not a Euro graph. This for these two pages, we transfer the graph to a Hoffman graph. So I may introduce slightly more what is a Hoffman graph. A Hoffman graph is a pair of graph and a labeling map. A labeling map give a labeling of vertices of H to two different classes. Let's say part of the vertices of H is labeled by F, and the other is labeled by S. The condition is that every vertex with label F is adjacent to at least the Y vertex of label S. It means that a vertex with label F cannot be an isolated vertex. And the vertices with label F are pairwisely non-adjacent. That's it here. we asked these T vertices are paired with non-adjacent. And we see the vertices labeled by S slim vertices, and the vertices labeled by F fat vertices. And if every slim vertex has a fat neighbor, then we say this Hoffman graph is fat. And because the Hoffman graphs are very new definition, so I will give graphs to show what are Hoffman graphs. Here, the left one is the Hoffman graph with two slim vertices. I draw them with somehow very slim. You can see that the vertex is somehow very small. So, and I draw the fat vertices with larger or big vertices. This is how we usually draw Hoffman graphs. Here, the left is a Hoffman graph with two slim vertices and 5 fat vertices. And we can check the definition that every fat vertex is adjacent to a slim vertex, and the fat vertices are pairwise non-adjacent. So this is a Hoffman graph. This is a Hoffman graph, and the right side is also a Hoffman graph. The Hoffman graph is defined. The definition of Hoffman graph occurs in a paper by Wu and Neumaier in 1994. In that paper, they used the Hoffman graphs to study graphs with smallest eigenvalue slightly less than -1 minus square root 2. So, but the idea to use Hoffman graph to study graphs with fixed smallest eigenvalue first occurs in a paper in Hoffman in 1976. I want to say here is when Hoffman graphs is introduced at the beginning, it is used to study graphs with fixed smallest eigenvalue and very large valence. So I want to say Hoffman graph is somehow useful to study graphs with fixed smallest eigenvalue. And we have Hoffman graphs, and we must, if we want to use it to study smallest eigenvalue, then we must define some metrics related to Hoffman graph, as we have adjacency matrix for Euro graph. Here is the matrix related to Hoffman graph. Assume that H is a Hoffman graph. We denote by VSH the set of vertices of the set of slim vertices of H, and then we have the matrix related to Hoffman graph, and we call this matrix special matrix. The definition is as following. The special matrix SPH, it's symmetric, but it does not have 0 on diagonal. It does not have all 0 on diagonal. On the diagonal entries, let's say XX, the special matrix has the opposite of the common neighbor, the opposite of the number of fat neighbors of X on this entry. Let's say the common neighbor, the fat neighbor of X. And for the off diagonal, let's say XY, if these two vertices are adjacent, then this entry is Y minus the number of their common neighbor. And if these two vertices are not adjacent, then it's the minus of their common fat neighbor. There are several ways. Okay. Here I give an example. It's better to use the example to explain or to show the special matrix. Here we have a Hoffman graph, and it has two slim vertices. If we look at the picture, so the special matrix is 2 by 2 matrix. Let's say that for every slim vertex, it has exactly 2 fat neighbors. So in the special matrix, its diagonal entries always has -2, and for the off-diagonal matrix, as this 2 vertex is adjacent and has 2 fat neighbors, so the off-diagonal is 1 minus 2. This is the special matrix. We see the eigenvalues of Hoffman graphs are the eigenvalues of its special matrix. And as for graphs, we use lambda minimum h to denote this smallest eigenvalue. There are many ways why we define special matrix this way. And here I give few reasons. The first reason is that if this Hoffman graph has no fat vertices, then we can regard H as a Euler graph or original graph. And in this moment, its special matrix and the adjacency matrix are the same. This is the first reason. And the second reason is that if H prime is induced Hoffman subgraph of H, then its smallest eigenvalue is not less than H. This is the second reason. And the third reason is also an important reason, but I'm showing it here. No, I put this reason here, but we may not need it later. At least in this talk, we will not use the third reason directly. The third reason says that if we have H, the Hoffman graph H, we can replace each fat vertex F by a clique of order n, and join all of the fat neighbors of this fat vertex to all of the cliques, all of the vertices in this clique. Then we have a graph. And this graph's smallest eigenvalue is not less than the smallest eigenvalue of H. And once the clique, I mean that the replacing clique is very large, then the graph's smallest value has the limit let's say the limit of this family of graphs is the smallest eigenvalue of H. This is how we use Hoffman graphs to study graphs, but I will not use this property of special matrix in this talk directly. And there are some more reasons why we define special matrix in this way, but it's out of this talk, so I will not have the definitions. I will not have the properties here. Until now, we goes from graphs to associated Hoffman graphs, then to Hoffman graphs. Then But at the beginning, we want to study graphs. So we have to find ways to go back to graphs. Then how do we go to graphs? Here is how we go back to graphs. This result says that give a real number lambda, give a finite family of Hoffman graphs with the smallest eigenvalue less than minus lambda. Let's denote this finite family by H. Here, it must be finite. If it's infinite, then we cannot have the following. And we have M to be the minimum and prime, such that the tilde graph K2M prime has the smallest eigenvalue less than minus lambda. The restriction on or the definition of M is natural because we only on when the graph tilde graph is not a induced subgraph, we have the associated Hoffman graph. So the third condition is also a natural condition. Then the result says that we can find an integer capital N related to M and this finite family, such that for any graph G with the smallest eigenvalue at least minus lambda, and any integer N, the associated Hoffman graph does not contain the any Hoffman graph in H as an induced Hoffman subgraph. This is how we give a relation between Hoffman graph and the graph. It means that if the graph has smallest eigenvalue at least minus lambda, if we choose N very, very large, then the associated Hoffman graph is also not allowed to have induced to have Hoffman graph with smallest eigenvalue less than minus lambda as an induced Hoffman subgraph. This is the result. This is the result in the paper by Professor Koolen and Qianqian in 2016. In that paper, they gave this property, and this is also this is also very okay. This property is let's say it's somehow like the fundamental property we need to study graphs. Now we give all we need and finish the preparation. Now I'm going to finish the last part of this the last step of this part and give a sketch of the proof and shows how we use the Hoffman graphs to show the result. Because we spend quite a lot of time to give the to introduce the associated Hoffman graph and the Hoffman graphs, we may forget what we want to prove. So here I reminded the main result we want to show again. So we want to show that we can find the constant kappa y, such that if a sesqui-regular graph with parameters vkc and the smallest eigenvalue at least minus lambda, when the valency k is very, very large, then either v minus k minus y is bounded, or the parameter c has a precise upper bound. And to prove the main result, we have to say what we have now. This is what we have. This is the first result about sesqui-regular graph with fixed smallest eigenvalue, but in this talk, we assume that it's proved in the previous paper, in the paper by Qianqian and Koolen. So I just regard this result as a known result. Known result says that we can have for sesqui-regular graphs with fixed smallest eigenvalue, either the parameter C is bounded or V minus K minus Y has this bound. So to prove this main result, we will use this result as a known result. So when we start to prove, we can assume that C is at most C2 lambda. Otherwise, from the known result, we have the first directly. So when we start to prove the main result, we assume that C is bounded by C2 lambda and prove that C has a more precise bound if K is sufficiently large. The proofs has 4 steps. As I said before, we want to use the associated Hoffman graphs to prove the result. So we first need the graph K2M tilde. So as we have before, we assume that M is such a minimum number. This is we usually have in this talk. And when I give the quizy clicks, I already say that if we have very, very large click, then or if we have very, very large n, then in every quizy click, any 2 vertices in this quizy click must have many common neighbors, because in a quizy click, we say that let's remind what's the definition of quizy click. A quizy click starts from a click of order n, and a vertex is in this quizy click. It has at most m-1 non-neighbors in this click. So if we choose the order of this click very, very large, then any 2 quizy clicks must have at least a-2 m-1. They have, let's say that they have many common neighbors. So it means, but we have an upper bound for C. It says that in every quizy click, it must be a click. This is what we can have from the condition a graph is sesqui-regular. If it's not sesqui-regular, we don't have this result. We don't have this property on the quizy click. But if we have, but now we assume the graph is sesqui-regular. So in this case, we can always choose large enough and such that every quizy click is a click. This is the first step. The second step is we want to say that when we build the relation between associated Hoffman graph and the graph, we say that if a graph has the smallest eigenvalue at least minus lambda, we can choose very large n such that the associated Hoffman graph does not contain induced Hoffman subgraph with smallest eigenvalue less than minus lambda. So this is the step. So this is the step 2. We found a finite set. Let's say it's a set with 3 Hoffman graphs. We know that if n is very large, then the associated Hoffman graph does not contain these three as the induced Hoffman subgraph. Because it's not hard to calculate that this three has the smallest eigenvalue less than minus lambda. This is the easy part. Before going to the next step, I want to say, let's say what are these three Hoffman graphs? The first Hoffman graph is y slim vertex adjacent to lambda plus y fat vertices. This is the first one. The second one says that y.
Sorry, excuse me. You have like 3 minutes left, like about 3 minutes left. So
sorry.
You might want to wrap it up a bit.
Oh, sorry. I thought, oh, sorry.
It's okay, it's okay. No, I just want you to know, like. Okay,
I thank you for reminding me. The first one is y vertex with lambda plus 1 fat neighbors. The second one is y with lambda fat neighbors, but it has a neighbor. Its neighbor has a different fat neighbor. And the third one says that is a large clique with lambda times lambda minus y plus y clique. This clique has a common fat neighbor, and there is y vertex adjacent to this clique. This is step 2. Then the second step is we choose a very large clique, because in the previous 2 steps, because in the 2 previous steps, we always ask for very large n. So in the third step, we choose, if we want the large n, then we choose very large clique, very large valence, such that the RV vertex is in a large clique, as we introduced before, because this graph does not contain the claw graph. The third step is to choose very large valence. Then this is the first step. The first step is we look at the associated Hoffman graph, and there are 2 cases. The first case is we look at this associated Hoffman graph and choose a slim vertex, because if we want to show the result, if we want to show our main result, we want to show that in this associated Hoffman graphs, the 2 slim vertices has distance to in G, has at most 6 common neighbors, has at most lambda square times lambda minus y common neighbors. Because of the time, I will only show the case 1. The case 2 is slightly more complicated, but it's not. Here I will show the example. Case 1. Case 1 says that you choose a slim vertex x, and every slim neighbor of x is in a same quasi-clique as s. Then in this case, we choose a vertex 1, which has distance 2 in J. Then in the step 1, we have known that every quasi-clique is a clique. So if these 2 vertices has distance 2 in J, then it's not in a same quasi-clique. And now we choose a quasi-clique containing X, and see how many neighbors Y can have in this quasi-clique. And from this graph, we knew that Y has at most M times M minus 1 neighbors in a clique contain X. And in the third step, in the third part, we know that every vertex X has at most lambda quasi cliques contain S. So the second one says Y has at most lambda times lambda minus 1 neighbor in each quasi clique. And the third one says X can be contained in at most lambda quasi cliques. So we see that X and Y have at most lambda times lambda minus 1 common slim neighbors. This shows that in this case, C is at most lambda square times lambda minus 1. And in case 2, it's slightly more precise. It's slightly complicated, but not hard. So I will skip the case 2. This is how we show the bound of C. And now I'm going to the last part of the talk. From the main result, we know that for sesqui-regular graphs with fixed smallest eigenvalue, if its valence is very large, we can say that either V minus K minus Y is bounded by this number, or C has a precise upper bound. And so we want to use this result to study more precise sesqui-regular graphs. For the case lambda is 2, it's related to the line graph, generalized line graph. So we skip the case lambda is 2 and goes to lambda is 3, and we showed let's see what will happen. For the case lambda is 3, we can say that the main result becomes when the valencing of sesqui-regular graph is very large, then either V minus K minus Y is at most 2, or C is at most 18. So it's anyway, the number is very small. So we want to see whether we can go further step or not, and we tried and succeeded. So for the case lambda is 3, and we give a classification of sesqui-regular graphs, and we proved that when the valencing is very large, then the sesqui-regular graph is in these 3 classes, or C is at most 8. It's better than the previous result. This is the classification we did for the sesqui-regular graphs, and now this paper, we put this paper in the archive, and now this paper is under review. So we have 2 more questions. The first question is when lambda is 3, what can we do for the sesqui-regular graphs, or what is the classification for the case where C is at most 8? Because in the previous page, we gave a classification for C is at least 9. And we want to do more. We want to say what will happen when C is at most 8. And another natural question is, what can we do with the Hoffman graphs for other graphs with good combinatorial structure and fix the smallest eigenvalue? Sorry that I did not control my time well and may prepare too much in this talk. Okay, now my talk is over. Thank you.
Thank you, Cynthia. Very nice result. Okay, so is there any question for Cynthia?
Okay, so I just wonder like what kind of other like graph you have considered, like try to use the same technique to give her like a similar bond, because you in the last question you mentioned like good combinatorial structure, like what exactly like
yeah, actually okay, let's go back to the slides. Oh. Okay. In this talk, we talk about sesqui-regular graphs. Somehow it likes to remove the third condition for strongly regular graphs. Like we have 1, 2, and somehow like 4. We study such graphs, and now we are consider another classes of graph. It has the condition 1, 2, 3. It means that the two adjacent vertices has fixed common neighbors. We are studying this class of graphs called AGT graphs.
Yeah.
And we are giving some characterization on this kind of graphs with fixed small eigenvalue. My meaning is strongly regular graphs with 1, 2, 3 without 4.
Okay.
Yeah, but we are still doing it, and now we don't have a precise result. So.
Okay.